During my PhD research, I worked on efficient sampling techniques with applications to radar detection. The problem I address is to deal with huge amounts of data, which is actually a problem of our time. In fact, modern sensors produce huge amounts of measurements to obtain data with very high resolution. Think, for example, of a digital camera that in a few years went from 1 to 15 megapixels resolution. But in fact, this is also the case for many other systems, such as MRI scanners, ultra-wideband communication systems, pattern recognition, and also for radars. For example, modern airborne radars use multiple antennas and very high sampling rates in order to achieve high-resolution images of the ground. This results in an amount of data per second that is comparable to the size of a movie, and therefore is very difficult to store or to process in real time. As this problem occurs in many areas, in the last 10 years, a lot of scientists started to investigate an alternative to the current state of the art in sampling. These efforts led to the development of a novel sampling theory known as compressive sensing, which provides a framework to reduce the amount of samples needed to achieve a desired resolution. During my PhD research, I exploited this theory to both enhance radar capabilities and to reduce its size and costs. And indeed, I was able to demonstrate that detection of radar targets can be performed with significantly less data. Also, I designed a novel radar architecture based on compressive sensing, and I demonstrated its feasibility with a practical experiment. The outcome of my research will have an important impact in the development of future radars, as it will allow the design of systems that are cheaper, faster, and better. Finally, I would like to conclude by saying that women in science can perfectly be both successful scientists and great mothers. Thank you.
Hi, my PhD project concerned increasing the amount of oil produced from underground. When gas and water are injected to push the oil out, a significant part of oil remains behind, whereas foam injection, which is gas plus water and surfactant, produces more oil. But how to predict the behavior of complex foam flow? I demonstrate in my thesis how one can reduce the huge computational effort of modeling such a three-phase, four-component flow of foam with two-phase flow methods. This work is so fundamental that is now used in one of the advanced master courses. The other big challenge is to bridge different length scales, the millimeter scale within the foam front and the meter or kilometer scale in the overall displacement. And likewise, different time scales, the seconds of length in foam dynamics versus years in overall displacement. Our innovative mathematical techniques to solve this problem are applicable for any displacement with finite rate kinetics involved. Moreover, I proved two general beliefs of foam society to be wrong. First, tens of papers discussing the effect of foam dynamics in foam front, which I proved has absolutely zero effect. And second, I disproved a popular simplifying assumption in foam simulation. Finally, the most applicable question is also answered in my work. Is foam able to propagate to far distances from the injection well, or it fails and leaves oil behind? My work also explained the result that had gone unexplained for 25 years. And surprise, surprise, the explanation is not what was expected. And all this happened in an interdisciplinary environment, working with two supervisors, and an engineer and a mathematician. Bridging this gap, of course, was a huge challenge per se. And in 2012, one of my 6 papers won the Best Shell Paper Award, and finally I graduated cum laude in less than 4 years. And I am proud to wrap up my pitch with a proposition of my thesis. women must consider twice as much on an everyday basis. Luckily, this is not twice as difficult.
My doctoral research was about the capability approach, an influential normative framework. The values central in this approach are well-being, agency and justice. And these values are conceptualized in terms of individual capabilities, what people are realistically able to do and be in life. Examples are the capability to be healthy, to be part of a community, or to travel around. And this capability approach provides a lens through which one can look at new technologies and arrive at an ethical evaluation of how they impact human lives. So if you take a simple technical artifact like a speed bump, it limits the capability of car drivers to speed, but it also expands the capability of other people to safely move around town. And until a few years back, the application of the capability approach to technology had hardly been studied. Last year I edited a Springer volume, the first book to have appeared on the topic. I was also co-founder of a thematic group under the umbrella of the HDCA. That's the Human Development and Capability Association. And I organized their 2011 conference in the Netherlands with innovation as its theme and almost 450 participants. And through these kinds of initiatives, I have contributed to a growing research community on the capability approach, technology and design. This has all been made possible by a grant from NWO, for which I wrote the proposal myself. And this grant of €550,000 also financed 2 other PhD students. They are working on design for poverty reduction in the Global South and look into the practical implications of the capability approach. Whereas my own part of the project was more theoretical in nature, what I've done is confronting the philosophical literature on the capability approach with existing design theories and technology approaches. And the result was a deeper understanding of the relations between technology and those valuable human capabilities. For example, one can argue that Facebook does not merely expand our capability to be part of a community, but it also changes our understanding of what it means to have such a capability.
Good day. Thanks for letting me present my PhD research to you. I aimed at reducing an everyday problem for many of us, congestion. This can be done using measures such as informing drivers about the best route and reducing the flow onto a freeway with traffic lights. However, to apply these measures effectively, we need to know where and when traffic jams will occur. And we need to know this quickly. I have developed methods to make such predictions, even in uncommon situations, such as after an accident or in the case of an event. Traffic can be predicted using traffic flow models. Almost all traffic flow models include a fundamental diagram. It shows one of the most important properties of traffic. If there are more vehicles on the road, the throughput is higher, but only to a certain limit. If the roads get too crowded, the flow decreases. This distinguishes traffic networks from many other networks. For example, if the pressure in a pipe increases, the fluid flows faster and the outflow is larger. This difference makes modeling traffic flow interesting. But the change of increasing to decreasing flow also makes it challenging. I have developed an alternative way to model traffic flow to deal with this challenge. If we look at traffic from a different perspective, namely that of the driver, the fundamental diagram takes a different shape. If the distance between the vehicles increases, they will drive faster. Now the fundamental diagram is always increasing, just as with fluid flow. Using this approach, I have developed a new traffic flow model, fast lane. I have analyzed the model and compared it to similar models. Finally, I have applied the moving observer approach to develop more efficient simulation methods to predict traffic flow quick and accurately. With all this in hand, and together with 2 other PhD candidates, we have delivered a software tool that is available online. It uses real-world data to predict traffic and to determine the best measures to reduce traffic jams.